Heave a heavy sigh. How's it going? Hello, hello. Turn off my recording. Oh, do y'all have any particular stuff you want to talk about for the review? Sorry, I'm just getting Twitch set up over here. Hi. You have one particular question you would like covered. That sounds fantastic. Can we cover some of the third exam? Yeah, sure. We can do that as well. Yeah, I was surprised. All right. Let's do, Nate, what's your specific question? We can do that one, and then we'll sort of talk about exam 3. Oh no. So that sounds like it was already a tough topic. Oh, so it's from the midterm also. That works. Okay. Let me pull up the midterm. Oh wait, no, you wanted the midterm and you wanted test 3. Okay. Do I have a copy of the midterm? Surely I have a copy of it somewhere. Okay. Midterm question 2 from part 3. Okay, the 3 blocks connected by a massless wire over a pulley, is that it? Yeah. Okay. Can I? Okay. Might be. Okay. Boop. All right, can y'all see it? Okay, and a question from Ben on Twitch about question 4 in the homework. Okay. So I'm gonna, Ben, I'll get to yours in just a second. Okay, so Nate, this one was your question. Tell me about how you approached this when you took the test the first time. You can turn on your mic if you prefer to talk than type. That's fine too. Hi, Dawson. Hi, Dawson. Okay. You assume a free body diagram. That is a fantastic idea. Okay. So one thing I like to do is ask students, like, what category of question do you think this is? So we've talked about a lot of different topics. I just realized I forgot something. So, like, is this kinematics? Is this momentum? Is it energy? Is it forces? Is it Newton's third law, Newton's second law? Is it circular motion? If we had to put this into a category, what would that category be? So, definitely forces and tension. Okay. So one thing to think about for questions like this is, are there several objects interacting, or is it just like one object with some forces acting on it? So this is kind of the question, is this more of a Newton's second law or more of a Newton's third law? I mean, really, it's kind of everything is both, but objects interacting. Okay. So how many objects do we have? So that's a question. 3 objects, possibly 5 with the ropes. So that's a really good question about the ropes. The ropes are technically separate objects, but they are massless. So we don't really have to consider them as their own objects, but that's a good thought. So we definitely have 3 objects. So that means, how many free body diagrams do we need? I'm going to hold this down. It's getting annoying. Okay. Oops. 3. Okay. 3 free body diagrams. Okay, so I'm going to have one for mass M, one for the 15 kilogram, and one for the 10 kilogram. Okay, which one do you want to start with? And this is really easy because all the forces are vertical, right, up and down. Draw a dot, draw a dot. Okay, let's start with 10 because we have, the most information on it. Okay, so tell me the forces that are acting on the 10 kilogram object. Gravity and tension. So how much is the force of gravity? Force of gravity is mass times 9.8. So this is 98 newtons. And then we have tension is 133 newtons upward. And that's it. There's not really anything else. So from here, we can answer a lot of these questions, but I think we should keep going and do the other free body diagrams. What about the 15 kilogram? What are the forces on that? That's easier. 2 tensions and gravity. Yep. So we have the 133 is now downward. Make that a little longer, right? So 133 is the tension, which means it pulls up on the lower block and down on the upper block. 133 newtons. We also have the weight of itself. Ft is 15 times 9.8, which is Am I doing the math? No, I cannot. 98 plus 49, is that right? 147, yes, that's what it was. So I have 139, which is the rope. I have slightly longer, 147, which is the weight of the block. And then I have a tension. There it is. Tension upward T, but we don't know what that is. Okay, so far so good. What about mass M? Okay, good. Gravity and tension. Okay, so we don't know the force of gravity on this one because we don't know the mass. And we have tension. Okay. So I have a question. We have essentially 3 or 4 things that are tension. We have this one, we have this one, we have this one, we have this one. With the T being the same as the T in the 15, correct. These two are the same. These two are the same because that's how massless ropes work. They pull the same amount on each side. Is that T equal to 133 or is it equal to something else? Something else. Good. Because this is a different rope, right? There's different ropes have different tensions. Okay, so we know it's not 133. Okay. We have some beautiful free body diagrams. If you got this far, hopefully you got a bunch of partial credit. This is about where you were stuck. Okay. So, other folks, do you have any recommendations for what we should do next? Is there anything we like to do for force-related problems? No suggestions? Acceleration of the system? Yeah, we can do that. We can apply Newton's third law to each object and to the system. For the system as a whole, you have a force of gravity mg trying to pull it sort of counterclockwise. You have 15g and 10g trying to pull it clockwise, and the result of all those forces is going to be our total mass times our actual acceleration. We have 2 unknowns in this equation. So that's tricky. So what I'm going to do is, I like this chart. I line up all of my forces, and then they add up to be the net force. And we only care about the y direction, so I'm going to only deal with the y direction for this. Doesn't want to let me draw. Only care about y. So For M, we have force of gravity plus tension in wire A are going to equal the net force. The force of gravity is mg downward, so I'm going to call that negative j hat. The tension in the rope is some number upward, TA, and together they add up to the total mass times its acceleration. Okay. I can do the same thing for the 15 kilogram. I have its force of gravity, tension in wire A, and the tension from the other mass. Those have to add up to F net. So this is going to be negative 147 newtons. This is going to be an upward tension. This is going to be a downward 133. And when I add those three together, I should get the 15 kilograms times whatever its acceleration is. Okay. How do these two accelerations compare? Is this making sense so far? The objects are not assumed to be in equilibrium. That's part of the tricky stuff here. I think a lot of students assume that it was balanced, but it's not. Do these charts make sense? I find these really useful, but it's hard to know if students find them useful. Okay, kind of. Okay. So Dawson, does it make sense to think about it as for M, we have T upward minus mg downward equals its mass times its acceleration. And for the 15 kilograms, it's that tension upward minus 147 downward minus 133 downward equals its mass times acceleration. So we're applying Newton's second law. Okay. Some people find it makes more sense to write it this way. Some people find it makes more sense to write it that way. Okay, what about these two accelerations? Are these the same? Are these different? Are these opposite? Are these double halved? What's going on here? They should be, since they're connected, okay? So they definitely are going to be the same magnitude, because if the big mass goes down 1 meter, this mass has to go up 1 meter. So that means that one of these is going to be negative. So what I'm going to do is I'm going to take this one and say, so this is A15, this is A15, this is AM, this is AM, right? But I know that AM is just negative A15. So I can replace that right here with negative A15. Replace that here with negative A15. Okay. So now I have two equations, but how many unknowns do I have? 3. I don't know T, I don't know M, I don't know A. Let's do it for the 10 kilogram. That has the 133 upward minus 98 newtons downward equals 10 kilograms. What about this acceleration? Is that the same? Is it bigger? Is it smaller? Is it opposite? Yep, equal to A15. So really, I can just call all of these A. It doesn't really matter. Yeah. be a system of equations, but it's not actually even that hard because look at this last equation. How many unknowns are in this equation? 1. 133 minus 98 newtons equals 10 kilograms times A. So this is 35 over 10. So our acceleration is 3.5 meters per second squared. All right. So Nate, you can run on ahead if you want, and I'm going to keep asking Michael and Dawson. I got a positive number. Does that make sense? Well, if we look at our forces, I had a bigger force pulling up than I did pulling down, so it makes sense that it would be accelerating upward. So that means this mass has to be accelerating downward, which means this has to be heavier. It's got to be at least 25 kilograms. Okay. And hey, look, that's the answer to part A. What's the acceleration of the 3 blocks? 3.5 meters per second squared. Done. Okay. Now what? Tell me what to do now. So this is part A. Solve for t in the above equation. So we take this number and we plug it in right here. No. So we have t minus 147 minus 133 equals 15 times 3.5. So this tension has to be great enough to accelerate the 15 kilogram mass upward at that rate, overcoming both the other weight pulling down and its own weight. Okay, so then we do some math. Plus 133 plus 147, and we get T is equal to 332.5 newtons. Hey, that's part B. Okay, now what? We only got one unknown left. Let's solve for it. What's the mass m in kilograms? We go back to that first equation. Okay, so for the first equation, we have T up minus mg equals m negative 3.5. Right. Negative is important because that's the difference between it accelerating upward and accelerating downward, right? The math doesn't know what you mean. You have to know what you mean. Okay, so we found T up. This is 332.5. Okay, minus m times 9.8 equals m times negative 3.5. So we're going to move that over. 332.5 equals m 9.8 minus 3.5. So we get minus 3.5 is 6.3. So this is m times 6.3 meters per second squared. 332.5. 32.5. Oops. Divided by 6.3, and I get 52.8 kilograms, which makes sense. I hoped it would be bigger than 25, and it is bigger than 25. Okay. Okay, does this make sense? And then the second question is, how would you know that this is the right way to do it? Right, so those are kind of the two halves to solving physics equations. Do you know how to do it? And do you know which way is the way that you're supposed to do it? Tell me how it's going. And then Ben, while they're thinking, so I pulled up the goat question. So that's the one you had a question on, right? The goat. So the thing for that, I'll put it over here to the side. Goat question. It actually specifies the heights are measured from the goat's lowest point. So what happens is you have a spring, and then you compress the spring down 1.2 meters. And this is y equals 0. And then you put a goat. It's definitely what a goat looks like. Right? And then it asks what happens at 0.6 meters. So at 0.6 meters, it's like half sprung. And then it asks what happens at like some other distance, and then what happens at its peak. Ben, did that help over in Twitch? Is that like picturing it a little bit better? So the 1.2 you're really using to help you with your 1/2 kx squared and your kx. Yes. You don't care about the total length of this spring, you care about how much it was squished from its normal length. Yeah. Okay. All right. So Michael says free body diagrams are very important. I think I get the process now. Good. I'm glad you get that makes sense. So, okay, can any of y'all tell me why students don't want to draw free body diagrams? It's something that I've seen in every class, and I don't know why. It's not physically painful. It helps you solve the problem, but students never want to draw it. Tell me why. How can I convince you to draw a free body diagram? It's a mystery. Maybe it takes too much space on the paper. Maybe. So on these things, you can do it with, you can use as much paper as you like. Yeah. What we should start doing is being like, you get 5 points for a free body diagram. No free body diagram, no points. But ramped problems are tricky because then you have to do trig. Yeah, true. You also have to do trig for like a rock on a string type questions and pendulums and things like that. You gotta do a lot of trig for that. But draw a free body diagram. Okay. Okay, let's talk about how did we know? How did we know what to do? Because there's sort of two steps. There's what do I do, and there's how do I know that's what I do? How do we know what to do? So I tend to recommend thinking about, so step 1, use brain, right? This is my underappreciated first step to solving all physics problems. Read the question, look at it, imagine it in your head. Your brain is more powerful than almost any computer that exists. Let it help you. if it, like, skipping over stuff is how you cause problems for yourself. So sort of read it carefully, imagine what's going on. One thing I also like to recommend is to ask yourself, like, what if questions, which is like, what if the M mass wasn't there? Read the damn question. Yes. Professor Burbank is on my wavelength. Yeah, read the damn question. I understand though what happens is that your adrenaline is going and it's on a test and you're like, oh my God. And then you think you recognize it and you're like, oh, okay, you can do this. And then you go. And then you didn't actually read all the problem and it's asking you something different. So I've actually had tests in the past where you had like 5 minutes where you weren't allowed to write anything down. You just had to read it. But I don't know if that actually helps. So, all right. So what if questions? Like, what if there were no big mass M? What if the tension in this was 0? What if these two were balanced, the 133 and the 98? What would that mean? Right? Why did they give us this information? Does it have something to do with the question, or is it a red herring? I don't like red herrings. I try to eliminate them, but it's a valuable thing to ask yourself, because it might be like, okay, wait, I know this doesn't matter because everything falls at the same rate, so they gave me the mass to confuse me. But asking yourself, like, why did they tell me this? Draw. This might be a diagram. This might be a free body diagram, right? But draw something. Sometimes I can tell that a student is interpreting the question wrong. So I had a student, there's a question on the final homework where it's like a rocket that's launching upward through a hoop. And the student had drawn it with the rocket sideways and the thing was going this way, when the rocket is supposed to be upward and the hoop is like right here and it's supposed to like go upward, right? And that was like, oh, okay, now I understand why you did what you did. It's not that you don't understand physics, it's that you didn't understand the problem, which means it's a badly written problem. So you will get more partial credit if you draw something and I can tell, like, oh, I see what you did. You thought the goat was under the spring, right? And then 3, I tend to think about categorize. Like, you think about, which topic is this? Are there hidden rules? Are there hidden knowns? Like, oh, hey, this is a free fall problem. That's hard to read. I know that it must be accelerating at 9.8 downward. Oh, this is a momentum problem. Oh, I know that momentum is conserved in this system. Oh, it's a collision problem and it says it's elastic. Oh, I know the momentum and kinetic energy are conserved, right? It helps you figure out what do you know, and then it helps you figure out which equations are relevant. These kids playing around outside, pretty cute. So, like, am I doing Newton's second law? Am I doing momentum? Am I doing impulse? Like, what am I doing? Okay, so those are like my 3 steps that I like to encourage. If you do those 3 steps, I feel like you'll get pretty far. All right. Does anybody have any other questions? Or I know Michael wanted to talk about exam 3. Let me pull that up while you're thinking. Exam 3. Let me paste. Okay, long response. Long response is tough because it's often a harder question and it's worth more points. So that is a really challenging area for a lot of students. It'd be nice at one point just to get like a quick refresh on the bigger topics. That makes sense. So then I want to offer one resource for you, which is, let me find it. If you go to Canvas, I'm trying to pull it up before I have to log in. There's two things I want to point out to you that might be useful. One is, share my screen. It's not the right class. No, I don't want that class. I want this class. This one. If you look in modules, final exam resources, there's a thing that says things to make sure you know for the final. So this is like a summary of those kind of big ideas, sort of various how-tos. There's a lot of them. So it's hard to kind of do a review of all of it, but I can try. There's also, if you look at the syllabus, a very detailed list, chapter by chapter, of everything you're expected to do. So that is a great way to be like, hey, can I do this? Can I do this? Can I do this? We did not do 15, so don't worry about it. And we only did part of chapter 12. Nobody ever gets to chapter 15, but our boss won't let us take it out of the syllabus. It's been 5 years. No one has ever covered it. Okay, so Ben, hopefully you will find this helpful. If you want, after we talk about exam 3, we can talk about some of these if you want, or we can just like whiz down it and give like 30 seconds for each topic. So, whoops. Okay, let's have a look at test 3. Okay, Michael wanted to look at the long response. Part 3, okay. So 3 long response questions. There's the block at the top of the hill. 2 automobiles traveling at right angles. And taking your neighbor's child to the carnival. Okay. Switch colors here. Okay, make this a little bigger. Okay, let us apply our 3 steps. Number 1, 3 steps. Step 1, use brain. Okay, what did I say under use brain? Read, imagine, what if questions. Why did they tell me that? Okay. So, read the entire question. And then think of okay, that's a thought. I should make little review things for each of those topics, but I'm not going to do that in time for tomorrow. Circular dynamics and torque are a lot of students' weak spots. It's very true. We can talk about those at the end. Also, number 3 here is like circular dynamics bonanza. So for number 1, can you imagine in your head what's going on? Okay, so we have a block sits at rest at top of a short hill. Short hill, there's a block. Total of some amount of work is done and it reaches some velocity. So maybe it gets pushed, somebody does work. Then it goes down a ramp. Usually when things go down a ramp, they go faster. Then it enters a rough section. Okay, what happens at a rough section? Things usually slow down. And then it eventually comes to a stop. Okay, so you have like a mental idea of what's going on. Some of the things that they give us in the problem, 0.68 joules, 1.2 meters per second, 0.39, 1.52. Why did they give us this specific information? Yeah, you did pretty good. Like, there's an equation on the formula sheet that is not appropriate in this situation, but it's close enough that I had a hard time taking up too many points. Okay. And all of these need to give us H. Okay. So can we think about like, okay, how do these connect to our situation? Why do you think they gave us 1.52 meters? If it were a bigger number, what would be the change in the situation? Aha. Hi, John. John over on Twitch says, if 1.52 were greater, that would mean that it went further before stopping, which meant it was going faster, which meant that H must have been higher. Right, exactly. Mm-hmm. Yeah, velocity would be larger. What about the 0.39? How does this play into it? So if 0.39 were bigger, tell me what you think. Distance traveled is smaller, yes. So this means there would be more friction. So it would travel less. If it traveled the same amount, that would mean it had to be going faster in order for it to stop in that greater distance with more friction, right? So H would be higher. So does this kind of make sense how we're connecting the information they give us to the information that we want, right? So we definitely need to use this. We definitely need to use this. What does this make? What about 1.2 meters per second? If 1.2 meters per second were greater and everything else was the same, what would that mean? No thoughts? Well, if it still took 1.52 meters to stop, then it had some V initial here that was the same. If V1 is bigger, that would mean that the ramp added less. Yeah. So H is smaller. Okay, so that means we have to consider the difference between the energy it has right here and the energy it has right here, or the speed that it has right here and the speed that it has right there. Okay. And then our last thing is this 0.68 joules. This one's a little tricky. Why did they give us this? This one is a little bit subtle. The purpose there is it gets us the mass. If we had the mass, we wouldn't need it at all. So this is kind of like the initial push. These are both sort of connected together in terms of the initial push. The harder you push it at the beginning, the more speed it's going to have. So if it's traveling the same distance, that means you added less from the height. Okay. All this makes sense. So, okay. Do you think this is like a helpful way to organize how you're thinking about the problem? So our next step would be to draw a picture or a free body diagram. Yay, good. We already have a beautiful picture. Do you think we need a free body diagram? It never hurts to draw one. But we have some different stuff going on. So at the top, our free body diagram would just be normal and gravity. And then there's some push that we don't necessarily know about. And then it goes down the hill, there's normal and gravity. And then it's coasting along with just normal and gravity. And then it hits the rough patch. Now we have normal, gravity, and friction. What kind of friction do we have? This is a really terrible drawing. Oops, I deleted my hill. Kinetic, yes. Okay. So 3, our next step is categorize. So what did I talk about for categorize? It was think about which topic. Are there any hidden knowns? Any particular equations that we want to be thinking about? So, okay. So what topic or topics do you think this covers? Let me scroll back up so you can see the question. Okay, work, energy, kinetic energy, friction. Hooke's law is for springs. I don't see any springs in this one, John. So, yeah, but work, kinetic energy, friction. Mm-hmm. Okay, so work, energy, friction. Okay. Is there any particular approach or any particular equations that are especially, there's one I think that they gave to other students that had a Hooke's law in it with a spring, but we did not. So do we have any particular like approach that we want to do or a particular equation that we want to use? You can also think about, can this problem be divided? Can this problem be chopped up? Sometimes students try to do the whole thing in one step, but you actually have to do like, okay, this bit and then this bit and then this bit. And then sometimes you have to do them in weird orders, right? What do you think? Yes. I know I do tend to ask like 6 questions at once. So yes, it can be chopped up. I mean, presumos, yes, it can be chopped up. Yeah, so I would divide it into a before ramp, and then friction sections. And think about them kind of separately. So the before piece is the 0.68 joules applied to make it go to 1.2 meters per second. The ramp is our unknown H. The friction part is our 1.52 meters and our 0.39. And we already talked about, okay, well, if the 1.52 was greater, that would mean it was going faster. So do we have a way to get the speed? And then we can use these two and use them to get H. So, all right, we think about just friction. I have a thing that slides 1.52 meters where my mu k is 0.39. Oh, hey, I know how to do this. This is mu k mg. And then my net force is just my force of friction, which is mass times acceleration. So I end up with my acceleration is mu k times g. And then I know from kinematics, v squared equals v squared plus 2a delta x. This is what I'm looking for. This is 0 because it stops. Equals v squared plus 2. This is my mu kg. This is my 1.52 meters. And I can solve for my v initial. And I don't even know what number I get. I get something. I went through that kind of fast. Hopefully that made sense. But basically what I did was I cut it into a question that was a lot simpler, and I know how to do that. Like, that's an easy friction question. Times 9.8, 352 times 2, square root, 3.4. Okay. So no, it was going at 1.2 meters per second, and then it was going at 3.4 meters per second. So using that information, I can figure out the height of the ramp, because I have figured out how much energy that the ramp added. When we're talking about the ramp, there's no friction. We handled the friction separately. No potential energy. There's no external ropes or external work. So mgh plus 1/2 m the 1.2 squared equals 1/2 m times the 3.4 squared. And then we can solve for h. Okay. Tell me how that feels. Scale of 1 to 10. You're like, okay, I totally get it and I know how to approach these problems in the future, or I get it, but I don't know if I can do this by myself. What do you think? Okay, John's at an 8. Excellent. Yeah. So how did I know I wanted to do conservation of energy? I didn't have to. I could have also done kinematics or forces, but knowing the speed before and after, and I'm trying to get the height of the ramp, that's a pretty classic conservation of energy question. Yeah. And we had that as one of our possible topics. We ended up using energy and friction when we were doing this. Okay. How about Nate and Dawson? How are y'all doing? Can I do this like here? No. Hmm. You're just multitasking. Okay. Okay, let's look at the next question. Can I highlight this? Can I select stuff? I don't think so. Just scroll down to get some new space here. Oops. 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 None of those are what I want. All right, fire. That's not what I wanted. I wanted that. There we go. Okay, let's look at number 2. Ah. Okay. Whew. Copy. Paste. Piece of crap. There we go. Whatever. Yes, it can't be super long because I have another thing, but it can be, yeah, chat a bit. The final will be more similar to the problems on the final homework, or will be a few problems from each test. Okay. It will not be problems from previous tests. I would say it is about 30% like stuff from the final homework, so like torque and energy, and then like maybe a little more than 30%. And then the rest of it is like problems from all the different topics. So it is comprehensive. And it will generally not be questions that have been on previous tests or homeworks. All right, so we have 2 automobiles. Can I just copy this whole page? Technical problems here. Paste. Yes, okay. Number 2, 2 automobiles traveling at right angles to each other. I'm gonna put up the 3 steps. Use brain, draw, categorize. I mean, studying past tests will be helpful because, like, if you don't know what you did wrong, you're probably going to make the same mistakes again. But I would say that it's the same level of helpful as studying previous homework, and studying, like, doing new problems. So I personally think doing new problems is the best way to study. Yeah. Okay, so we're thinking about using brain. So we're doing some like imagining. Okay, I have an automobile, right angles. They're traveling at right angles to each other, so it's like kind of like this, like a T-bone. They collide and stick together, so they're going to go and then move together. Car A has some amount of mass and some speed. Car B has some amount of mass. And then it tells us the wreckage was moving at a certain angle with the original direction. Okay. What is the speed of car B before the collision, assuming any other balance forces were negligible? Okay. So hopefully we have all imagined this correctly. We have 2 cars kind of T-bone and then they go off together in some other angle. The knowns that they give us are the 1,200 kilograms, the 25 meters per second, the 1,600 kilograms, and the 40 degrees. And then we are trying to use these to find the initial V for car B. Okay, so how would that change? Well, if car 1 were heavier, then it would tend to dominate. So you would expect it to almost keep going more like, you expect it to go off at almost a shallower angle, right? So instead of going off of 40 degrees, it might go off less than that. Same if it was going faster. For the mass of the other car, right? The more massive it is, the kind of the further it would push the 40 degrees. It would be more like 50, and it would be going faster. So, I like to draw a picture. Okay, so we have car A. Definitely what a car looks like. Draw a DeLorean, that's the only type of car I can draw. Okay, traveling this way. And then we have another car traveling this way. Really, I should do them both from above. That would make more sense. Okay, so this is 1,200, 25, this is 1,600, this is unknown. And then they stick together into one crumpled combined thing, and it goes at an angle of 40 degrees from the original path. Can you draw a Cybertruck? Oh gosh, those are super ugly, aren't they? I don't even know what they look like. I'm just like, it's like a box. And then it's got like I feel like that's what it looks like. Totally accurate. They're your generation's DeLorean. Okay, does this picture make sense? This picture is what you were imagining in your head. Okay. And then our third step is to categorize. What are some topics or equations? Do you recognize this somewhere? Like what chapter might this be? Is this forces, kinematics, energy, momentum, circles, torque? Momentum, yes. So we can identify this as a momentum problem. Okay, what do we know about momentum problems? We know momentum is conserved in an isolated system. Is this an isolated system? Usually collisions are, yeah. So we know our momentum is conserved. We also know that momentum is a vector. So we have to care about direction. Okay, so we're pretty sure we're going to do a momentum conservation problem. Is there any particular equation that we should use? Probably the conservation momentum. But and they stick together. Okay. All right, so let's go look at our knowns. We can really easily see where we plug in these three things, right? Those are all pretty obvious. Oh, 1200 is going to go here. 25 is going to go here. 1600 is going to go here. This is our thing we're looking for. This becomes 2800. But this V I don't have. And I have a thing I didn't use. So stuck. So then we think about, okay, is this 40 degrees important? Yeah, because the faster the truck goes, the sharper the angle is going to be, right? So we need to use the fact that it's 40 degrees. Okay, so how can we use that 40 degrees? There's like a bunch of different ways to do this. You have to split it into components. Yes, split what into components? Final velocity vector. After they collide, write two momentum equations for x and y. Yes. Sorry, my thing fell down. Separate x and y. So our final velocity v, I can separate into vx cosine 40 and vy. Oops. Vx equals v cosine 40, vy equals v sine 40. Okay, and then I can have two momentum conservation equations. m1v1x plus m2v2x equals m1 plus m2v, cosine 40. Aha, that's much better. So I've still got my 1200, my 25, 1600. What's this Vx? Look back at my situation, 0. Hey, I only have one unknown. I can solve for V. Final, V final. And then I can do this for Y. V sine 40 where this is 0, I can plug this in right there for v, and then solve for the initial speed of the truck. Okay. So does this make sense in terms of like, if I don't know what to do, what are some like questions I can ask myself? Right. One of them was like, I drew a picture, I did momentum. Okay, I'm missing something and there's something I haven't used. How do I use this? Do I need it? Yes, because it makes sense physically that it would make a difference. And then I have to figure out a way to use it. It helps you like get rid of the red herrings, and anything that's not a red herring, you've got to use. Okay. How are we doing? Do you want to look at the third one? Or if you have other questions, we've spent a lot of time on just a few things. Looks like Nate's disappeared. I don't know about Ben. What time will we be on tomorrow? Tomorrow I'm thinking 11 a.m. to 1. So hopefully that'll let people who have an exam at 1 participate into the original equation. So which original equation? In this equation, you have sort of mashed up x and y. These are all really vectors. So what you want to do instead is plug it into the separated x equation and y equation. Yeah. It's tricky. I would say 90% of students did 1200 times 25 plus 1600 times v equals 2800 vf, and then tried to solve for v, but it doesn't work because it's two-dimensional. No. Right. So this is where the things you know about momentum comes in. Momentum is a vector. A lot of these problems on the final homework feels like I'm doing it right, but I'm going to check it, see if it's right. It isn't. I have no idea what I'm doing wrong. That's really tough. So let's talk about that really quickly. Wrong answer. Now what? So that's a really good question. Okay, let me finish Michael's thing first. I'm unsure where to put. So let me do this in a little more detail right here. I did sort of skim it. So momentum is a vector, which means we have to separate x and y. So we need an m1v1x plus m2v2x, and these are the initial values, equals m1 plus m2 v final x. And our v final x is our v final total cosine 40 degrees. Then we have a y equation, m1 v1y initial, m2 v2y initial, m1 plus m2 v final sine 40. Yes, you put it in the y component equation. And so where it gets interesting is that this is 25 meters per second, but this is 0 because our car is traveling horizontally, but our truck is not traveling horizontally. Well, okay, let's say this is east. This is not traveling east at all. It is making no easting. That is a technical nautical term. No easting. So that's 0. And then in this equation, this is 0 because our car is not traveling north, but this one is. So this is our initial speed of the truck. And these two are just the magnitude of the final speed, so they're the same. Yay. Okay. Wrong answer, now what? So don't panic. Right? And don't shotgun. So what I mean by shotgun is what happens sometimes is the students are like, okay, well, this didn't work, so I'm just going to try a bunch of totally random things and see if any of them work. That may eventually get you to the correct answer, but it will not help you know how to do the problem. So I would say your steps. Look for math errors. So a lot of this happens in calculators. So kind of go through it and make sure. No shotgun. You need a good backstop if you're going to fire a shotgun. You don't have one. Look for math errors. Look for units. Like, is like millimeter and like kilometer, things like that. Did that mess you up somewhere? There is, especially if you're pretty sure you're doing the approach right. Those are some things to look for. Another is, did I plug in the right stuff? So for example, I was grading a Physics 2 test the other day, and a student had just misread the mass, and they had put in 75 instead of 70. So their number was off. Everything else was right. So check that you plugged in the right stuff and check where you plugged it in. So another thing that happens is like, oh, you plugged in 25 for Y instead of X. So one thing is to kind of be like, why did I do that? You're like, okay, well, why did I choose to do momentum? Well, because it's a collision problem that's usually momentum. Why did I choose to separate it into X and Y? Well, momentum is a vector. Why did I plug this in as 0? Okay, because it wasn't traveling in the X direction. Why did I do this random thing? I don't remember why I did that random thing. And then another thing you can look for is faulty assumptions. Did I assume that it was an equilibrium, like a problem we talked about earlier? Did I assume that it was accelerating and it's not? Did I assume that these two things were the same? Or missing assumptions, right? Is it an equilibrium and I'm not including that information? And then if none of that works, I think what I would do, oh, and then another thing is reread the problem. Make sure that that's not, you're like, oh, it's going backwards, right? And then what I might do is walk away, do something else. This works for homework, not so much on a test. And then start again from the beginning. Because what sometimes happens, I've had students who had this problem in Physics 2 especially, they just kind of erase and rewrite and erase and rewrite and erase and rewrite. And by the time they're finished, they don't know what they did wrong and they don't know how they fixed it. So your logic is more important than the right answer. If you write the right answer on your paper, okay, you might get a small amount of credit for doing that, but you have not actually learned how to do the problem. And the shotgun approach and just randomly erasing stuff is a great way to confuse yourself. Okay, will the final be the same length as the other exams? Yes. It's actually, I think, yeah, about the same length. We cut quite a bit because we really don't want time to be an issue for this. So I think it's shorter than the midterm, although I'd have to check. Open. There we go. 4 points. Okay. I'd say it's about the same length. Yeah. Multiple choice, short response, and then a few long. Yeah. Mm-hmm. There are some practice finals, I think, on Canvas. There's also some PowerPoints that have a lot of really good, like, conceptual questions for practice. Because multiple choice is another place where it's like, ooh, this is from fall. So ignore the stuff about how many questions there are, but it has a bunch of like practice. It's like 20 something problems. Oh, this one that everybody got wrong on chapter 3. How would force balances pull gravity on the water? Everyone got it wrong, which means that that's my bad, that I am not explaining this correctly. So this is, you can actually play kind of the same game. It's like, why are they asking me this? Well, they're asking me this because this must be related to some physics concept that we talked about. And it looks really simple, which means it's probably one of those things that students get wrong all the time. So I wouldn't say it's necessarily a trick. The correct answer is false. Why is it false? Why is it false? It is accelerating downward, which is actually kind of part of the trick. So if you have things spinning in a circle, right? Well, you have like a water bucket, right? At the top of its path, I drew it badly. So water, water. Why doesn't the water fall down? So kind of the issue here is like, okay, is there some sort of force that's pulling it outward? No, it's inertia, right? It's the quality of things to keep going in the same direction. It is accelerating downward because it's traveling in a circle. But it is like if you put a hole in the bucket, right, what would happen? It would spray water everywhere. Why would it spray water everywhere? Is there some force that is pushing it out? Not really. What's happening is that at the location of the hole, there's no force holding it in. Not pushing out. The natural thing water wants to do is keep going at the same direction that it was going originally. If at any point I cut the rope, the whole bucket is just going to go in a straight line. Because there's a force sucking it that way? No, because things want to keep going in the direction they're going, and the force is what's keeping it in. Without that force, it's just going to go whoosh. It's a really tough one, and everybody got it wrong, so that's it's a tricky one. All right. Anybody got any more questions? It looks like I've lost everybody on Teams except Michael. I don't know who I have on Twitch. Oh, I have a few people on Twitch. Okay, problem 3 in the module 3 exam. So that one was this truly delightful, like, swing. Paste. Okay. Take your neighbor's young child to the carnival. So, our steps. Use brain. Draw. There's already a pretty nice picture. And categorize. And you don't necessarily have to do them in this order. Okay, we have your neighbor's young child. She wants to ride this ride. Rockets hang by chains from the outside edge of a large steel disc. So usually they hang down like this. Vertical axle spins it, so it's rotating around. Cars revolve in a circle. If you've ever seen one of these carnival rides, what happens is the cars swing out to hang at, so really this would be lower. And then as it goes faster, it rotates, it swings out. So now it's not quite straight down. Okay. Disc is 6 meters in diameter, chains are 6 meters long. When the ride has reached its full speed and the cars swing out until the chains are 20 degrees from vertical, how fast is the neighbor's child traveling? Okay, so you are given some information, but not a whole lot. That's kind of it. You're given the 6 meters, you do 6 meters and 20 degrees. That's kind of it. And then you're supposed to find V, her speed. Speed is tangential velocity. Okay, so, how are these connected? Well, it seems like the further out the faster it goes, the further out it's going to swing. So the 20 degrees is definitely going to play into it. And how does the 6 meters play into it? Well, you can imagine that if it was a much bigger thing spinning at the same speed, would that make a difference? Kind of does. Okay, draw. We've got a picture. What about a free body diagram? Is a free body diagram appropriate for this question? Well, can we categorize it? What type of question is this? Definitely circles, but is it kinematics or forces or both? So this is one where you might have to think. It's both. Yeah, pretty much. It has to involve forces because there's no other kinematics information. So you've got to use the 20 degrees. Why does the 20 degrees matter? Because it has to do with the angle of the tension and the angle of gravity. So I would say a free body diagram is definitely appropriate. We have gravity pulling down, we have tension holding it in, and that's it. 20 degrees. We know that it involves forces, so we think about what do we know about circular dynamics? There's one very key idea, which is centripetal force. F net equals mass times centripetal acceleration. And the centripetal force is not its own thing. It's just a regular force. Right? So in terms of our free body diagram, and it points inward, what is our centripetal force in this case? The x component of the tension, exactly. Tx equals MAC, Ty equals Mg. How are Tx and Ty related? Well, they are both, we have to be a little bit careful here because our 20 degrees is here. This is going to be cosine 20 for our y direction. This is going to be sine 20 for our x direction. So we know T sine 20 is the mass times our centripetal acceleration, which is v squared over r. T cosine 20 is mg. And then you solve the system of equations. I just divide, and I get tangent 20 equals v squared over rg. And then you end up with v is the square root of rg tan theta. So some of this is recognition in the sense of knowing what type of thing it is. Not necessarily, oh, I have done this problem and I can do it again, but like, I recognize the concepts that are in play and the strategies I need to use. Sorry, my throat's starting to get dry. Length of the rope for the magnitude of the tension. The length of the rope only plays into it in terms of finding R. And most people got R. So this is 3 meters, this is 6 meters, and then this is 6 sine 20. So you end up with R is like 5.05 meters. That's all it's for. It's little things that get you. It's the little things that get you when you weren't paying attention. There's a song. Okay. Phew. All right, ¿qué pasa? How's it going? Anything else? Definitely look at all this stuff on Canvas because there's a lot. Beautiful PowerPoints. There's some practice questions from previous exams. Yeah. That's a video from a previous test. And then I think there's stuff in the recitation section as well to help you study. Oh, there we go. Practice tests and keys. I knew there was practice tests in there somewhere. Oh. I'm happy to just chill. Okay. All right, Michael, you wanted to chat afterward. If nobody else has any questions, then I might end the stream and we can chat. If you're still interested. People on Twitch, tell me how it's going. Let's stick in teams because we're already there. So Twitch, I'm going to say going once, going twice. Nobody has anything, although Twitch lags pretty hard, so let me check. Infinite nesting, Twitch. There we go. All right, so by now I think Twitch has had their opportunity, so I'm going to stop the stream. Thank you so much for coming. I'm going to end the meeting on Teams, and then Michael, I'll send you a message on Teams. All right, thanks y'all. Good luck. Happy studying. Stream.